Visible, is this okay? Audible also. Okay. Thank you all for coming. The title of this work is Differentially Private Release of Spatio-Temporal Data Statistics. And all of this is based on work that was conducted at India Urban Data Exchange, or IUDX, which is actually located inside IIC. Okay. So there are a lot of players in this work, a lot of contributors, and I'll go over each of them in turn. The first among these is Dr. Anshu Tandon, who is the Director of Research at IUDX, under whose aegis much of this work was conducted. The second important contributor possibly in the sequence is Prajwal Gupta, who was an intern at IUDX, I think about 2 years ago. And much of the work that we'll speak about in the first half of the talk is based on stuff that was done by him, simulations that were conducted by him about 2 years ago. Then there's Novanil, who's sitting here. So Novanil Chakraborty at IUDX is a senior software engineer. And he's in charge of what is called the data anonymization pipeline. I will not be speaking about that in this talk, but this talk is about something else. Then, of course, there's Aditya Vikram Singh of IISc, who's a PhD student here. And we have Dr. Abhay Sharma, who is the CTO of IUDX. So now that the introduction is done, what is this talk about? So it is, at least now it is well known in the computer science community that if one were to release even seemingly innocuous functions of a particular non-public or private data set, it is possible in principle for one to glean some information about the identities of individuals who are present in the data set. And many works have shown over at least a period of about 2 decades that this is actually possible for very, very simple functions like this, like the mean, like counts, and so on. And so in order to alleviate such problems, the framework of what is called differential privacy was introduced by Cynthia Dwork and co-authors, and about the same time by Erik Denor and Kobi Nassim, I think in 2003. And this lays down a principled framework for the analysis of algorithms that are private in some semantic sense. So in this talk, for the first part, I'm going to go over some basics as to what differential privacy is, primarily because the audience is from mostly a comms background. And then we'll be going over some algorithms that we have designed with a view towards making certain things in practice private. And I will not be going into too many details as to how these algorithms work, but I'll only be giving you the high-level ideas. All right. And needless to say, there's been an explosion of work since the 2006 paper. Some of these I've just collated here. At least on the theory side, you have the famous discrete Gaussian for differential privacy that very recently won the PETS, something like a test of time award. It was authored by Clément Canon and other authors. And you also have tiny differential privacy, concentrated differential privacy, and so on, which are extensions of standard differential privacy. And on the practice side, you have seminal works like those authored by Abadi and co-authors, which is called DPSGD. You may have heard of this. And you also have other works called that are based on generative adversarial networks, PATE, GAN, and so on, which seek to make black box machine learning algorithms differentially private in some sense by implementing stochastic gradient descent in a differentially private manner. So that is the key idea behind those works. And there are many more works, and even Even today, if you check archive, there are at least 2, 3 preprints that have been posted on differential privacy. It continues to be a hot topic of research. Okay. But this talk is not going to be about standard differential privacy. We're going to take it one step further. And in particular, we're going to talk about something called user level differential privacy. So where does this user level come about? Most real world applications like federated learning, image recognition tasks, traffic data sets, and so on, have many contributions from each user. Okay, so we should really think of a data set as consisting of users and the samples that they contribute. Okay? And each user can potentially contribute multiple samples. And the number of samples contributed by different users need not be the same also. This is what is called heterogeneity. So very recent work by Levy and co-authors formally defined what it is for a mechanism or an algorithm to be user level differentially private in some sense. I'll tell you what that means. So broadly speaking, this ensures the privacy of a single user when he or she contributes potentially multiple samples to a data set. Fine. And there are many works spawning off even today, at least in the machine learning community, as to how to apply user level differentially private algorithms for these stochastic gradient procedures and so on. Okay. So what is the setup of interest to us? The title of this talk is Spatio-Temporal datasets, right? So consider a city, the area of which has been partitioned into grids or hexagons. One standard way of doing this is using Uber's H3 indexing system, for example, which not just partitions the city area into hexagons, it also partitions the time of the day into time slots. And we are going to bin all samples contributed by users in a city into these grids and time slots. And we are, sorry, hexagon is just for tiling, just for covering the area in as efficient a manner as possible. It's just a feature of the implementation. Yeah, you can use different things. You can even use circles. But okay, so we're going to refer to a hat in this talk as being a hexagon and a time slot. Okay, so you fix a grid, you fix a hexagonal grid, and you fix a time slot of the day of interest, say 9 a.m. to 10 a.m. And you look at all the samples that were contributed by users in that particular hexagon and at that particular time slot. So that's what I mean when I say a hat. I'll also interchangeably use hats and grids. Okay, when I say grid, I mean a hat. Okay, and this is the data set of interest to us that we'll be showing you simulations on. This is what is called the ITMS or Intelligent Transit Management System dataset, and it is publicly available on the IUDX website for a particular Indian city. So what are our contributions in this light? The first thing that I'm going to be speaking about is about the differentially private release of the sample mean of, say, speed samples in one specific grid or hat. That's what you see on the top left here. On the top right, what you see is the joint release of sample mean and sample variance across different grids of a city simultaneously. Another contribution of ours, very recent, is about releasing what is called the approximate cumulative distribution function of one-dimensional samples that are contributed in a data set. I'm not going to be talking about this at all in this talk, okay, but I'll be pointing you to a recent preprint of ours that covers this material. So let's go to the first part of the talk. Again, some preliminaries. So fix a particular hexagon and time slot or hat or a grid, and let capital L be the number of users that are present in that grid. And let this collection ML be the collection of numbers of user contributions. So what do I mean by this? There are L users, okay? So user 1 contributes M1 samples, user 2 contributes M2 samples, so on. User L contributes ML samples. And what do these samples look like? These samples you should really think of as speech samples. That's a recurring motif. Now these speech samples are like user 1 contributes M1 speech samples, which are indexed, which are called S11 to SM11. Okay. So the index L here is really the index of the user. And the J that you see here is just a J that runs over the indices of the vector that has ML samples. So you have vectors of user contributions. And our interest is basically to just release this simple, yes. I will get to it. We mean something very, very specific. Okay. So the differential privacy framework only guarantees some such thing. I will tell you exactly what that is in about a slide or two, if it's fine by you. Okay, so let's just set the stage again. We want to release this particular function, that is the sample mean. So what does the sample mean? It's just the sum over all speed values that are contributed in the specific data set, normalized by the total number of contributions, just summation m. We want to do so in a user level differentially private manner. So what is user level differential privacy? So in this slide, we will tell you what differential privacy is, in particular what user level differential privacy is, and it guarantees only so much. I will tell you another semantic interpretation of this, and that is only so far as you can get with differential privacy. Any other interpretation of DP is potentially wrong. Okay, so let us just stick to the definition and see what it means. So we'll call two data sets D1 and D2 as neighboring if they differ in the following sense. So you have a data set D1, users and samples, users and samples. Now, if potentially all the samples of a single user are changed between D1 and D2, then we say that those two data sets are neighboring. Now, what differential privacy asks for is the following. So a mechanism or an algorithm M is said to be user level epsilon differentially private if the following condition holds. So I take the mechanism and I act on dataset D1 with it and say, suppose the output is Y. Then the claim is that the probability that this potentially randomized mechanism, randomized algorithm outputs this value Y when acting on dataset D1 is not too different from the probability that it outputs the same Y when acting on dataset D2. What does this mean? So just before we get to what it means, what is this e to the epsilon doing here? Really, you should think of e to the epsilon as 1 plus minus epsilon. Okay, so e to the minus epsilon, e to the plus epsilon, think of them as 1 plus minus epsilon. The reason you have exponentials is just for graceful cascading, okay, when you cascade several mechanisms together. Now coming to what this actually means. What this means, at least in a Bayesian framework, is that if you had an adversary who was given just the output of the mechanism. So the adversary is told this output comes from either dataset D1 or dataset D2. He doesn't know which one it is, but he knows what the output of the mechanism is. Then assuming a uniform prior on datasets D1 and D2, half-half, then the probability, the posterior distribution, that is the belief that the output was actually the output of the mechanism when acting on D1 is not too different from the belief that the output that he or she sees is really what comes from D2. So that's exactly, that's all that it says. So as you should think of this from a hypothesis testing perspective. This in a binary hypothesis test between two data sets, between two distributions, M of D1 and M of D2. The probability that you can distinguish between these two samples when given sufficiently many is particularly small. If you know from hypothesis testing, the probability of error is governed by e to the minus n times the KL divergence between them. And this essentially says that the KL divergence is at most epsilon. This is for the information theories. Okay. Sorry? Just Y. And the fact that the output has come from either D1 or D2. No other prior information. No. Just know that this is either D1 or D2. Y is not the mean. Y is just some output. The only difference is in the definition of the neighboring data set. Here, the neighboring data set, you could change multiple samples of a given user potentially. It seems like a relatively simple tweak, but there are some issues when you apply it in practice. So this is what we see. Okay. So that's all. It's all very well to define what user level differential privacy is, but it's another thing to actually achieve it. So how does one go about designing an algorithm that achieves user level epsilon differential privacy? So one canonical way of doing this is via something called the Laplace mechanism. What does this mean? So given any function f that you want to compute, say for example the sample mean, you define something called the sensitivity of that function. So what is that? That is really the maximum between the absolute value of the function evaluations at D1 and D2, where D1 and D2 are assumed to be neighboring. Okay, so that is just a definition, it is what it is. For instance, if the function f were the sample mean, then you have that the sensitivity is given by this particular expression. So it's u m star over summation m. What is m star here? M star is the maximum number of user contributions, max over all L ml. Okay. So what does this Laplace mechanism do? Given any statistic or function that you want to privately release, the mechanism takes the actual statistic and simply adds Laplace noise to this. Okay. The Laplace noise does not depend on the statistic in any way besides the dependence via the sensitivity. Okay, so sensitivity is a worst case kind of a definition because you have a maximum here. It doesn't tell you what the data set is. Mean average is what? Okay. I don't understand. Hmm. Oh, you mean the expected value of this? Sensitivity will be 0. Okay, yeah, there are instances where the sensitivity can be 0. Yeah. But you want to take the maximum, the extremal data sets. We will see what they look like. But this is an extremal notion. This is a worst case notion. Okay, so it's a maximum over all neighboring data sets. It's not just any which data set that is neighboring and then I take the difference. The difference can be arbitrarily small for any which data set. For the extremal data sets, they'll be large, potentially. So one standard fact is that whatever I described now is user level epsilon dp. Why? Well, all that you need to really verify is this fellow. And this you can verify by just computing the PDFs of the outputs. Okay. You take the ratios of PDFs of outputs of neighboring data sets and you get this fact. It's a simple thing to prove. But we are not just satisfied with privacy, we want utility also. What does utility mean? It just means that whatever we are outputting is not too far from the true value that we want to output. Okay, with high probability. So this is basically something like a concentration result. All that it says is that the Laplace mechanism, the output of the Laplace mechanism is close to the true statistic f of d with high probability. Okay, how close is determined by this guy here, which is delta f over epsilon, which is really the sensitivity over epsilon. Okay. So really what this tells us is that the sensitivity over epsilon, which in some ways can be thought of as the standard deviation of the Laplacian noise that you add. It's proportional to delta f over epsilon. If that is small, then you can estimate whatever you wanted to estimate with high accuracy. Okay. So just to see what that means, so the standard deviation of the noise that we are adding is roughly proportional to delta mu over epsilon, like whatever I say. And that guy, if you plug in the delta mu value, comes out to be so much. So the issue here is that in practice, when either of u or m star is particularly large, then the amount of noise that you're adding is large. So the entire goal of this conversation is to find ways of mitigating the high amount of noise that we are adding in order to ensure differential privacy by doing something clever. Obfuscate, yes. Yes. Recover. We won't denoise. We will just take the output and declare that as such. So that is how most differentially private mechanisms work. Yes. Yes. If you're willing to go up to this amount of error with sufficient amount of probability, then that is what that is what such a procedure can guarantee. Hmm. No, we can't assure that. True. You have to do that for all users. Let's say 100 users have contributed to the data set. No. So we are not directly perturbing the user samples. We are only perturbing, like you see here, we are only perturbing the statistic itself. We are not. So if you perturb user samples, then potentially, actually, if you normalize again, the amount of noise is going to, the standard deviation is going to remain the same if you normalize. Yeah. But if you aggregate, then you have a problem. The output looks, yeah. So in our belief, the output looks like this. And we are going to use that output itself as the value of FFD for further processing. So much. Yes. With high probability, it will be so much only. Yes. What are the values of epsilon and delta? Epsilon, yeah. So epsilon, as we'll see, we are really interested in smaller values of epsilon. You should think of epsilon as varying anywhere between 0.01 to up to 5, at most 5. Epsilon can be larger than 1. There's nothing that holds back epsilon from being larger than 1. The delta is up to your convenience. So that is, we don't specify how much that is. It's just a parameter. You plug that epsilon, you plug that value delta. I can possibly show you. Yeah. Sure. Okay. So now we have seen that just vanilla Laplace has some drawbacks. So how do we mitigate this is the focus of this talk, at least the first part of this talk. So the kinds of mechanisms that we'll be discussing fall into two broad categories. Ones that try to minimize U, the others that try to minimize M star, try to reduce M star. Okay. So how do you reduce U? You can do so by reducing the interval in which the samples lie. Because 0 to U is the intervals in which the speed samples lie. And I just want to clip that interval for some reason. I can reduce M star by clipping the number of user contributions, by clipping the ML values themselves. We'll see how these mechanisms work in practice, at least in the first part. So, but before we do that, we are really going to talk about a strategy for organizing samples from different users. Okay, so you need a data structure for working with these, for somehow computing these statistics. And one convenient data structure is the following data structure that we call a collection of pseudo users or arrays. It goes like this. You have a bunch of samples coming from different users. You start populating arrays in the following way. Okay, so you take the first minimum of ml m upper bound. So you fix some m upper bound, just some constant. You take the first minimum of ml comma m upper bound samples from each user, and you start populating arrays in a certain way. So you throw the first guy's samples into the first array. Then for the second guy's samples, the minimum of m2 comma m upper bound samples, you look for that array that is filled the most and you fill it there. We do it for a certain technical reason. I'm not going to go into why we do that. It's reminiscent of certain bin packing strategies, but we essentially do it in order to reduce the sensitivity of the overall function that we compute. Okay. Again, no details. But okay, so now we have a data structure. How do we go about implementing mechanisms on this somewhat fancy data structure? The first mechanism that we'll see is what is called array averaging. Okay, so this is something that we'll see over and over again. So it's good to keep this at the back of our minds. So you have arrays populated by user samples, right? So there are a k-bar number of arrays and each of them has samples. Now from these arrays, you first compute what are called array means. Okay, so I call them AI bar, which are array means, which are basically means of the samples present in each array. Then you take a mean of these array means and add Laplace noise to the final result and declare that as the output. It's very, very similar to the baseline mechanism. The only difference is you're potentially dropping some samples by organizing them into arrays. Okay. A bar is just the number of arrays. Correct. Yes, for potential gains in the estimation error in differential privacy. Not any of this. How would the adversary be able to figure out which user submitted which sample? I don't know. Correct. 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 In the data set itself, there are we do have indices. So for example, for speed data sets, traffic data sets, you can think of the index of every index that indexes every user as being some obfuscated version of his or her license plate. But different samples contributed by the same user have the same obfuscated value. Yes, that's all. Whose user you don't know. Yeah, which user you don't know. Potentially it's a permutation among all users, like a uniform permutation. But you don't want to even know so much is the point. Okay, so this is what array averaging is. Yes. Yeah. Same array can be shared by multiple users. Like for example, 1 and 3 share the first array here, simply because the minimum of M3, M upper bound can fit into the remaining space in the first array. Good question. We need to optimize it over some good metric of the array of the error. We'll see how we do that. Any other questions? Okay. So that is the first non-trivial mechanism that we have seen, array averaging. We're running greatly short on time. So the second class of mechanisms is like this. So first we saw how to basically just clip the number of user contributions alone in an attempt to reduce M star. Now, how do we potentially reduce U? We can do so by clipping the intervals in which these samples lie. So the broad procedure is like this. You have arrays, they have samples. Earlier we computed these array means, right? Which were means of the samples present in the arrays. Now you project these array means into some smaller interval. Then you take the average of those projected array means and add Laplace noise and declare that as the. That's all that there is to it. And there are two ways in which we do it. One called Levy, which has some complicated way of computing this interval of projection, some interquartile interval and so on. And we have some calculations as to what the standard deviation of noise is going to look like in this case, but details omitted. The second way in which we do this is via something called quantile. Again, a more sophisticated way of computing the interval of projection. Okay, that's all that there is to it. Again, we have some expression for what the amount of noise, the standard deviation of noise that we had is. You can ignore these for the results. So just a recap of everything that we have seen so far. We have the baseline mechanism that just takes a sample mean and adds noise. Then we have array averaging, which basically organizes the samples into arrays, takes the array means, the means of these array means and adds noise. Then you have these more sophisticated mechanisms that project the array means and then add noise. Okay, so that's enough of talk. Let's see how this works in practice. So we take the same ITMS dataset that I had originally mentioned, and then you just run each of these algorithms on the ITMS dataset. And clearly what you see here is that the baseline mechanism performs much worse than the other mechanisms. That's all that there is to say. But really all these mechanisms have been developed for IID data. So let us see how it works on IID data, synthetic data. Plot is, the plot is something that we call mean absolute error, which is really a Monte Carlo estimate of the L1 error across epsilon. Epsilon again varies from like 0.6, 0.5 to like 2.2 or something here. Really, that is one interval of interest. Correct. So some estimate of that error, the Monte Carlo estimate. In these units, it goes up to about 3.5. It all depends on the units. You can normalize to always, but normalization is just going to scrunch these curves together. Correct, because higher epsilon really says that your privacy requirement is less. So I'm adding less noise. Correct. Okay, so we also tested this on synthetic data sets by generating IID data samples and seeing what happens. The exact distribution of the data samples is something. It's like a projected Gaussian. So how do our algorithms work on synthetic data? The basic idea is this. We want to generate a large data set, so we do it in one of two ways. The first way is what we call sample scaling, where we fix the number of users L, but just scale the number of user contributions. So we have these ML values, right? M1, M2, and so on. We scale each of them by a large integer lambda. So that is what we call sample scaling. All the data samples are assumed to be IID. Then we plot the same MAE value. What we see here is that this sophisticated Levy mechanism, whatever that means, performs the best. But not too far away is the vanilla array averaging mechanism. So let's remember that. In the user scaling setting, where we fix the number of samples per user, we fix the ML values, but we scale the number of users. Okay, so we just take like IID copies of every user. There we see that a certain quantile mechanism performs best, but again, the array averaging mechanism performs second best. Interesting, because the array averaging is a very simple mechanism that does not clip the that does not clip the sample values. It just clips the number of contributions. That's all that it does. We have some explanation for what goes on here. So again, I'm not going to go. They are two different, correct. That's what is called fixed quantile. So in the quantile procedure that I just flashed, there were two subroutines. The two subroutines were essentially for finding the interval of projection. So we do it in two ways. These are basically just done in the literature, and we just employ this. Okay. So one is where we fix the actual quantiles. This is a 1/10th, 9/10th quantile. Something that we call epsilon dependent quantile tunes the quantiles themselves based on the epsilon value. And we have some function that we compute, optimize it over epsilon, find the best epsilon. Sorry, find the best quantiles for every given epsilon. Yeah. Correct. Everything is IID. No, you're right. Potentially non-IID, mostly non-IID, but this is just testing, just to get a feel for what these algorithms look like. Okay, so we have some explanation for why these things behave like they do. Again, not going into the details. The idea is to use something that looks like anti-concentration to prove these results. You can look at the paper in order to get more insights. Fine. So what was the takeaway? The takeaway was that array averaging performs not too badly. So we have very sophisticated mechanisms, but array averaging works good enough if we have some amount of error threshold. So let's study array averaging in more detail. So that was the endeavor that we took on. So let's see what happened at the end. So like Janaki pointed out, I think, see, it's somewhat wrong to assume that the data samples are all IID, especially in traffic data sets, primarily because you could have cars on one car that goes particularly slowly and everyone behind it goes at the same speed. So we are really working with arbitrary distributions of the data, okay? But we need some way of measuring this error in a reliable way, right? Amazingly, nobody has looked at, not many people have actually quantified non-IID distributions errors, okay? And this is our attempt at doing this, so let's see how it goes. So basically, we just chuck the entire distributional assumption on the data samples. We say, let us look at the worst case data set. What does that mean? For any given data set, we want a measure of the error under array averaging procedure. So what is array averaging? Is basically just clipping the number of user contributions, throwing away some user contributions, and then computing some function like the sample mean on top of these, right? So we incur something called the clipping error by clipping these samples, right? Clipping error is essentially the difference between the clipped estimator and the true estimator, no noise added. And then you have the error due to noise addition, which is essentially the error due to Laplace noise. Okay. So the way to think of this is really an upper bound on the L1 error. Okay. Why upper bound is because of the triangle inequality. It's also a fairly good, there exists somewhat matching lower bound up to a factor of half. Fine. So the magical thing or the interesting thing is that if you were to maximize this guy, find the maximum such error across all data sets, this is actually eminently computable. We can give you a proper expression for this, for the specific case of the sample mean being computed. Particularly the expression that looks like this. So the max overall data sets of this clipping error looks like some expression that is just a function of the number of user contributions. It's not a function of the data samples at all, as you would expect. Okay, so like she asked, what is the next task? That the next task is to find the optimal value to which you need to clip, optimal value of m upper bound. Now we have an error metric. We have an optimization problem that's literally written on its own. All that we need to do is to optimize over m upper bound, which is what this seeks to do. We do have, okay, we go about analyzing this optimization problem. We declare it as non-convex, but then we have some additional results to show about the optimizer, etc., etc. Again, no details. Please check the paper. The constraints are just that the m upper bound value that we want to optimize over has to lie between m lower star and m upper star. You don't want to like cut away all the samples. Yeah. So it's like a constraint optimization problem, but the constraints are simple. Okay, so again, what is the takeaway? The takeaway is we have a bunch of mechanisms, some more sophisticated than the others. But really, for the purpose of practice, if you have a sufficient error threshold, just use array averaging. Okay. Array averaging has additional benefits. You can actually compute the exact worst case error in a certain precise way and optimize that worst case error in order to find the best clipping strategy. Yes. No, I mean, so yeah, we did a bunch of things. We weren't able to actually make it convex in any way, like via change of variables. So we just analytically analyzed the that is eminently possible. That is easily done. But we want to get some analytical insight into this also. So we can just run like a Python program that sweeps over the m values, but from m lower star to m upper star, finds the best one as the solution. But really, if you want a structural, well, yeah. No, in fact, we could do the numerical thing. So we said, now that that is eminently doable, let's do the analysis. Fine. So this is the takeaway. Okay, takeaway in one slide. This is just the first part of the talk, so please stay on for more. So what have we understood? We have understood that if you were to release simple functions like sample mean, sample variance, and so on, it suffices to just clip user contributions. Don't clip sample values, so long as you have a sufficient error threshold. So now the question, an immediate natural question is, you have shown all this for one grid, for one hat. How does all of this extend when I want to release statistics over the entire city? So there are many hats in many grids in the entire city. Each of them has its own statistics corresponding to that particular grid. I want to release all of them simultaneously. So what happens then? More notation. So notation can be heavy, but let me just walk you through this. So the idea is just this. I'll show you a picture to ease the trouble. Earlier we had ML values, right? We had user 1 contributing M1, user 2 contributing M2, and so on. Now you have multiple grids, G1, G2, G3 up to G sub G. Okay. So essentially for every grid G, we look at M1 G1, M1 G2 up to M1 GG. Same way for M2. So that's what you see here as the MLG values. Exactly. We'll see what happens then. But just notation, just to set things. I'm not going to tell you what this means because I'm not going to speak much about these, but just think of each user potentially occupying multiple grids and contributing samples to each grid. So the samples are going to be indexed the same way as the ML values with a superscript G to the left. Okay. And the goal is again very similar. You want to compute now a vector, okay, you have your interest is in a vector of statistics. Each element in that, each coordinate in that vector is in fact a two tuple, one of which is the a mean, sample mean in that particular grid. The other is a sample variance in that particular grid. So it's basically, you can think of this as a 2G length vector, where G is the total number of grids, because each element, each coordinate has dimension 2. And we want to do this privately, obviously. So just a picture to these things. So users typically, you can't expect a single user to drive all over the city. So users, you can think of them as occupying a subset of the grids in every city. So user 1, for example, occupies 1, 2, 3 grids here. User 2 occupies 1, 2 grids here. User 4 occupies 2 grids here, and so on. Connectivity, not required for our analysis, is not required. Yeah, good point. Yeah. You would expect that the subgraph induced by each user is connected. True, but we want this vector. We want the statistics for every grid. Why, for example, why would we want this in practice? Suppose you were computing air quality index values, not just speeds. Okay? You want it for every neighborhood, and so on. You want call record statistics for every neighborhood. Okay, so yeah, just like sir said, what is one easy way to do this? Just apply the Laplace mechanism to every grid. That's all, end of story, right? So it seems. So you have the well-known canonical Laplace mechanism. You are given some function f, which is the concatenation of the mean, which is like mean comma variance. Add noise suitably, release this entire vector. So does that? So what are the issues here? So the first issue is that is in the computation of the sensitivity, but that is a technical thing. I'll just go over that. I'll just skip that. But the main issue is that is via something called composition. Okay, so what does this mean? You have a mechanism that you have for each grid. Importantly, the grids are assumed to be disjoint, which they are in practice, right? So you have disjoint grids in a city. You have mechanisms acting on these disjoint grids, releasing statistics. What the so-called basic composition theorem tells you is that if you nest all of these mechanisms together, or if you compose all of these mechanisms together in order to find one large mechanism, then that overall mechanism is G epsilon user level differentially private, where G is the total number of grids. Essentially, the privacy loss adds linearly in the number of queries that are asked. We are back to the same problem. Okay, we have a very large city. G is very large. Your privacy loss under composition is terrible. We don't. No, we are given that, no? We are given the statistics for every. So you're given a vector. Yeah. I mean, just the same way as the users. You could like mask the actual grid index, obfuscated in some way using a hash function or whatever. But you know that all the samples from having the same hash function have come from the same grid. Okay, so again, picture. You release all of these in a nested way. Okay, so you have a mechanism here, mechanism here, mechanism here, mechanism here. 4 mechanisms when put together is 4 epsilon differentially private. There's a problem because if you have very, very large number of grids, then this G epsilon value is particularly large, which means the overall mechanism is particularly bad in terms of estimation error. So can we do better? The basic idea is the following observation. The observation is that the grids in a city are all disjoint. So really the scaling is not by the total number of grids that are present, but by epsilon times the maximum number of grids that any particular user occupies. So suppose user 1 sits in the maximum number of grids in the city, then user 1 is your worst case guy. And the privacy loss under composition is just going to scale by G1 times epsilon, where G1 is basically the number of grids in which the user user 1 operates. So we could really seek to reduce this guy here. This is not fixed. This is not constant. I mean, in the following sense. So we should really try to trade off error for privacy loss under composition heap, which is the basic idea. So I keep saying error. So again, what does error mean to us? Again, the data sets are all non-IID. So the error to us is again the worst case error. How do we compute worst case error? There are any number of ways in which you can compute, you can aggregate worst case errors together across grids. But really, I'm going to tell you of the method that we used. So the basic idea is you have a worst case error for each statistic that you want to compute. Say, suppose you're just releasing the mean of each grid. Okay. So you have the worst case error in grid 1, worst case error in grid 2, worst case error in grid 3. You look at the maximum of these worst case errors. Okay, so it's like an L infinity norm applied to a worst case definition of an error. Okay. L infinity in the sense that you have a G length vector and you're looking at the maximum absolute value. You could even look at the L1 way of aggregating these errors. You could just look at the sum of these worst case errors and so on. It's up to you. But at the core of it is the fact that the worst case error is used for each statistic, for each grid. How you aggregate these statistics, how you aggregate these worst case errors across grids is up to you. But really, this is what we use. And this has a semantic meaning. All that it says is that you have a client who's asking for data. The client has absolutely no idea as to what the data set looks like. The client just knows that it comes from some data set. The client has some figure of error in his or her mind. So any data set unaware client should reasonably assign that error in his or her mind to the worst case data set. Okay, so this is the motivation behind this entire worst case business. Okay, so again, more technical details, not going to go over them, but we spend a lot of time explicitly computing the sensitivities of the clipped mean estimator and the clipped variance estimator. These are all somewhat sophisticated calculations, and they took a lot of space and time, but again, no details. And we also have explicit expressions for what these worst case errors for the mean and variance look like. Again, no explanations. They're actually pretty well-behaved functions. Just that calculating them requires manipulating proofs that have a lot of moving parts. Okay, so just some comments, at least for people who are interested in theory. Via our computations, explicit computations, especially for the sensitivity of the variance, we are able to actually improve on or extend the results that were known in the item level setting. And then people like really didn't do it for the user level setting. This is not a natural extension at all. The proofs are much more involved in the user level setting, but a special case of these is the item level setting. Just mentioned. Okay, so let's get back to our problem. Our problem is basically this. We want to reduce max overall LGL without hurting our error too much. What is our error? Our error is really the maximum overall grids of the worst case error in each grid. So we have this guy already fixed at the start. We don't want to go above that, but we want to reduce this while not going above that. So the algorithm that we use, again, I'm just going to summarize this for you, is like this. So you have the original worst case error that you started out with, right? Which is the maximum overall grids of the amount of noise that you would have added if you were just doing the Laplace mechanism. So any dataset unaware client is willing to tolerate a Laplace amount of noise addition per grid. Okay. Now you look at the maximum of this overall grids and declare that as your error threshold. And your goal now is to somehow improve the privacy loss under composition while ensuring that the overall error threshold does not exceed this. What do? So we want to reduce max overall LGL, right? We want to reduce the maximum number of grids that any particular user occupies. How does one reasonably do that? You could look at the worst fellow there. Say, suppose user 1 occupies 20 grids out of 40. And he's like driving all over the city. And you want to like really bring him down. He's contributing too much to the privacy loss under composition. So what you do is you throw away his samples entirely from certain grids. You completely suppress his contributions in certain grids. Okay. This is allowable because the number of users we are keeping the same. We are just throwing away his contributions in selected grids. Now we throw away his contribution. He has contributed just 2 samples in one particular grid. We throw away all of his samples. Now he sits in 19 grids. So now our worst case loss under composition is like 19 epsilon, something. But by doing so, we obviously incur a clipping loss, correct? Because we have thrown away samples there. But we know to exactly compute what the clipping loss looks like, remember? Because we had explicit expressions for those. So what we do is just this. We look at the loss post-clipping. So if we were to clip all of his contributions in a particular grid, if we were to completely suppress his contributions in that grid, how much would the error have decayed by? The error decays because there's a clipping loss now in addition to privacy. And then we look at the worst case error now, recompute the worst case error. Does it go above your error threshold? If yes, we stop. If not, we continue to clip. That is the essence of this algorithm. It's just a numerical procedure, an iterative numerical procedure. We do not have any analytical results about the efficacy of this algorithm, this particular algorithm. But we do have plots. So essentially for the ITMS data set that I was saying, this chap here, this blue curve, blue essentially line, okay, because the epsilon is in a log scale. So the blue line curve that you see here is the scaling of the privacy loss under composition with epsilon, originally without suppressing. And the red line that you see here is the scaling of the privacy loss under composition with epsilon post suppression. There's a clear gap. So this is, when we saw this the first time, it was almost like great to us, because in the item level setting, we are not allowed to do this at all. If you were to suppress a user completely, you're basically just throwing away that user. And your privacy loss under composition remains the same. It stays at 1 times epsilon. Okay. And it's also well known in the item level setting that you cannot do better than this linear scaling. It's a classical bound. It just tells you that the privacy loss under composition indeed scales as q times epsilon, where q is the number of queries in the item level pure epsilon differential privacy setting. But under user level epsilon differential privacy, user level is just an extension, but we do get some non-trivial artifacts from it. Okay, so clear gains. Okay, great. So that is really the end of what I wanted to say. So just to sum up everything that we have seen so far, we now know what differential privacy means. We have a definition, and we know that that is all the differential privacy actually tells you. Anything more is potentially spurious. Because there are many papers right now that are being written that use definitions that are supposed interpretations of differential privacy, but are not. Okay, so we know what DP is. We know what user level epsilon DP is. And we also know ways of achieving user level epsilon DP via something called the Laplace mechanism. What's more, we know something called the array averaging mechanism now. Organize them into arrays, take array means of array means, add noise. And we know that array averaging actually does fairly well in practice. And finally, what we have seen is that if you were to compose mechanisms across disjoint subsets of a data set, the disjointness is important. If you were to compose mechanisms across disjoint subsets of a data set, the privacy loss under composition can potentially be improved without increasing the worst case estimation error. Okay, so this is all based on the following works. We presented the first half of this at the ISIT ITTML, the information theoretic methods for trustworthy machine learning, and at the SPCom, and we have submitted the material on grids, multiple grids to the information theory transactions. We also have a recent work, if you're interested, on approximate cumulative CDF, cumulative distribution function release. It is somewhat more theoretical, much more theoretical than the second. It doesn't involve so many calculations, but it's going to resonate well with the comms community, especially because we use something reminiscent of the Viterbi algorithm in order to do something. Okay. And we have submitted this very recently to the TIFS journal, Transactions on Information Forensics and Security. Great. So where do we go forward from here? We're at IUDX on the research or algorithms front. We're really interested in differentially private clustering right now. This is about releasing cluster centers in order to make inference tasks possible, like telecom inference tasks and so on. Then we have other open problems that are of potential interest to theorists. We gave you some expressions for worst case errors for sample mean, sample variance. Can you guys actually do it for a much broader class of statistics, like counts in general, weighted counts? Then we'd be quite interested. We don't know right now. So the thing is, we're still framing the problem. No. We are only interested in like single statistics of a call records data set. For example, should I install a base station here because there are lots of people? Like counts. Count is a very simple thing, of course, but if there are more non-trivial statistics that are of immediate interest, please let us know. We'll also be interested in trying out DP variants of those. Any questions? It's really the end of the talk. Correct. So we have one really helpful lemma in differential privacy called the post-processing lemma. All that it says is that if you have a differentially private subroutine, any post-processing of that subroutine is differentially private. So if your stochastic gradient descent is epsilon differentially private, then any which machine learning task that you basically run that employs stochastic gradient descent is epsilon differentially private. Sure. Sure. Yeah. Yeah. Right now, we are not really looking for, at least I personally am not involved in the dataset collection task. Mhm. Ah, mhm. Link prediction. True. So yeah, 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 yes. There is a lot of work right now on differential privacy on graphs. Essentially, about if you have information on the edges of the graph, links, then how do you release that information or statistics of that information in a differentially private manner? So yeah, we are definitely interested. But these are still very much in there. No, none is yet. There are any other questions? Thanks.